Hi everyone, Dr. P here, and we're moving on into chapters 22 and 23, where we're going to be looking at reactions involving the alpha carbon of carbonyl and carboxyl species. So in this lecture, I'm going to introduce enols and enolates. So first, let's look at what we're dealing with here, and that is the alpha carbon. So the alpha carbon is this guy right here. This is our alpha carbon. 1 over from the carbonyl carbon, or the carboxyl carbon. You could have an alpha carbon for a carboxylic acid, let's say. And you can form what are called enols. And we'll have an equilibrium here. And in the presence of either acid, H3O plus, or OH minus and H2O, so either aqueous acid or aqueous base, we can get an isomerization to what we call an enol. So when we have the CO double bond, we refer to that as the keto isomer, and the alkene with the alcohol, that's where we get the name enol, alkene, alcohol, enol. The CC double bond with the OH, that is the enol isomer. And these are known as tautomers. Okay. Now, why are we interested in this alpha carbon? Well, it turns out that this electron density here makes an enol a nucleophile. It's kind of a weak nucleophile. There's a stronger version. And if we take a look at, well, let me just jump right in and talk about the acidity of the alpha hydrogen. And if we have something like R, C double bond O, C, H, H, R prime, compare that to R, C, C, H, H, C, H. pKa of that guy is around 20, and pKa of that guy is, I don't know, around 45 or so. So it's a much stronger acid than for an alkene if we had a carbon alpha to a CC double bond. And then the reason for that is the enolate ion. If we pull off this proton, what do we get? Well, RC, double bond O, lone pair, C, lone pair negative charge, R prime, H. Of course, we can have a resonance structure. I'll put in some arrows here to indicate electrons moving around. And that will give us now RCO minus on C, R prime, H. And again, we've got a keto form and an enol form, but this is the enolate. This ion is the enolate ion. And in this case, once again, we have a nucleophile here. And that full negative charge on that carbon, even though it is delocalized, we've got more electron density than we do in the enol. So the enol is a nucleophile, but it's weaker than an enolate. We'll just add that in there, weaker than the enolate. All right, so sort of depending on what we're dealing with, we may have reactions involving the formation of an enolate, or we may have reactions involving the formation of an enol. Typically, when we're in acidic conditions, we'll go via an enol type reaction. The enolate is only formed if we have a strong base. All right, so let's take a look then at the formation of enols. And I'll go over the two mechanisms, the acid-catalyzed and the base-catalyzed mechanisms. It would help if I could spell here, acid-catalyzed. All right, so formation of enols, acid-catalyzed mechanism. So we'll start with our keto species here. And the first thing we'll do is protonate, because, well, we're in acid, so we need to protonate. And that will now give us our C double bond OH, lone pair, positive charge, C H H R prime, and now water can come in and pull off the alpha proton, and we then get the formation of the enol. And there we go. So it's relatively straightforward. But you will want to be able to do this on a quiz or exam. Now, of course, there is a base-catalyzed mechanism as well. So let's take a look at that. We will have R, C, double bond O, C, H, H, R prime. And we'll start off with our base here. And we're using hydroxide because that's what I had in my, remember my original reaction here, had the aqueous hydroxide. And we will deprotonate. And that's actually going to give us species with a resonance structure. So we'll get our enolate ion, but I should draw my resonance structure here. And then if instead we go ahead and take that pair of, sorry, I just screwed up there. Don't worry about that. It's these electrons I want to take. Sorry about that, just a little mix up there. And now that will go ahead and give us RC, double bond C, prime, H, O, H. I was getting a little ahead of myself there. So you could draw either of these structures for the enolate. You could draw both of them. I mean, technically you would draw both of them because that would be the full, resonance structure indicating all the resonance structures. I think that the resonance structure on the left here really gets at the reactivity of the enolate, that our nucleophile is going to be the carbon. That's going to be our nucleophilic atom here. Whereas having a negative charge on an oxygen is more stable. So this resonance structure gets at the stability of the enolate. But anyway, so those are the mechanisms for forming enols in acid or in base, and of course in base it goes via an enolate ion. So things to remember from today, well, you want to know these mechanisms, then understand what the nucleophilic parts of enols and enolates are, namely the alpha carbon, because we have either extra electron density in the form of a pi bond, or we have a full negative charge. And then lastly, alpha hydrogens are acidic, well, relatively acidic. There is a table in the text. Let me find the table in the text here. Hold on. There's quite a table in the text, I think. Let's see where that is. Section 22.5. So table 22.1. So let me add that in here. See table 22.1 for list. And so I'll introduce some other pKa values for different alpha carbons and different species later on as we run across them. But just as a little reminder here, the alpha carbon or alpha hydrogen in, say, a ketone has a pKa of around 20. Compare that to, say, a nitrile, sorry, not a nitrile, an alkyne. A terminal alkyne has a pKa of around 25. An alcohol, like a substituted alcohol like 2-butanol, has a pKa of around 18. So it's only about 100 times less acidic than T-butanol. We'll see that if you actually stick another ketone over here, you can get an additional resonance structure, more delocalization, and an even more acidic alpha proton. All right, but we'll look at that in another lecture video. Okay, so that's it for this video on enols and enolates. Don't forget to practice your mechanisms, and until next time, stay safe out there. Bye now.